Imagine a snowball from another sun, older than our planets, gliding into the light of ours. It's not a spacecraft, not a myth, not a recycled piece of the solar system. It's an outsider, an object that formed around a different star, wandered for eons through the cold between suns, and, by sheer cosmic chance, has crossed our neighbourhood. Astronomers call it 3-Eye Atlas. The 3-Eye means it's only the third interstellar visitor we've ever confirmed, after Oumuamua and Borisov, and right now it's threading our planetary lanes on a one-time, never-to-return fly-through, offering a brief, electrifying look at materials and physics written in a dialect our solar system doesn't usually speak. It was first flagged in early July 2025 by the Atlas Sky Survey, those robotic telescopes that sweep the heavens every night, hunting anything that moves against the starfield. What tipped scientists off that this wasn't a local? Its path. 3-Eye Atlas is on a hyperbolic trajectory, not looping around the sun like a bound comet, but cutting across on an escape route, the celestial equivalent of a one-way ticket. That, plus its speed and geometry, marks it as interstellar. In plain terms, we're not watching a wanderer from our Oort cloud, we're watching a messenger from someone else's. Here's the heart-pounding part. 3-Eye Atlas reaches its closest point to the sun, its perihelion, around October the 29th to 30th, 2025. It won't dive into the inner furnace like a daredevil. Instead, it brushes the outer warmth at roughly 1.36 to 1.4 astronomical units, a little beyond Earth's orbit and just inside Mars's. That's close enough for sunlight to wake up its ices and dust, driving off gases and building that soft, ghostly coma and tail you've seen in telescope images. For scientists, this is the moment. Outgassing turns a quiet chunk of primordial stuff into a readable story written in molecules. If you step outside and can't see it, there's a good reason. The comet is tucked into solar conjunction during this window, essentially behind the sun from our vantage point, so Earth-based observers are blinded by glare. That invisibility isn't a failure, it's geometry. Once 3-Eye Atlas rounds the bend and the angle improves, it should slide back into the pre-dawn sky in early November, when amateurs and pros alike can resume the chase. Until then, space telescopes and specialised instruments do the heavy lifting. So what does it look like up close? Hubble's July images showed a classic teardrop haze, a cocoon of dust and gas lifting from an icy nucleus we can't resolve directly. That haze is our laboratory. Every molecule teased out by sunlight carries clues to where this object froze together. How far from its home star, at what temperature, in what chemistry. Interstellar comets are time capsules, and this one's lid is finally cracking. Big question people ask first, is it dangerous? Number. The trajectory is a clean miss by any practical definition. 3-Eye Atlas never comes close to Earth. Its minimum distance is about 1.8 astronomical units, some 270 million kilometers, later in December 2025. That's farther than our distance to the Sun. It's a scientific spectacle, not a threat. If you're scripting this for a wide audience, this is where you can let the tension fall away and let curiosity take over. Now widen the frame. We've only had 2 previous chances to study an interstellar visitor. Oumuamua didn't shed much gas, staying frustratingly quiet. Borisov did, behaving like a more typical comet. 3-Eye Atlas gives us the third data point, and 3 is the start of patterns. Do interstellar comets share certain ices? Do their dust grains reflect a different recipe of elements? Are there subtle isotopic fingerprints, ratios of carbon, oxygen, nitrogen, that tell us whether the disk it formed in was hotter, colder, or more irradiated than ours? Each answer tunes our models of how planets and oceans and atmospheres emerge around other suns. That's what the could change everything in your title really promises. Not apocalypse, but understanding. A better map of how common life's ingredients truly are. There's also the thrill of craft and coordination. While Earth-based astronomers wait out the conjunction, teams schedule space-based spectrographs, radio dishes, and thermal instruments like chess players, thinking several moves ahead. Once the comet emerges, coordinated campaigns will dissect its light across wavelengths, comparing lines in its spectrum to library fingerprints of water, carbon dioxide, cyanides, organics, and dust. The result isn't just a pretty tale, it's a chemical census. And because the object is interstellar, the stakes are higher. Its chemistry speaks for another planetary nursery entirely. If you want to give viewers a mental picture, try this. Our solar system is a crowded train station, planets marching on their tracks. Most comets are locals who loop in and out on long leashes. 3I Atlas is the traveller who steps off a train that doesn't stop here, glances around and is gone. We'll never see this exact object again. That's why the data we gather in the next few weeks and months, especially right after perihelion, as it reappears from the sun's glare, will be pored over for years, feeding into everything from textbooks to mission proposals. And if there's one line you want your audience to carry into the rest of the video, let it be this. We are, for a moment, in conversation with another solar system, not by radio, but by ice and dust, by sunlight and spectra, by a visitor from the void that reminds us the cosmos isn't a collection of isolated islands, but an ocean where frozen messengers drift between shores, bearing stories we're finally equipped to read. It started the way most cosmic surprises do, with a quiet ping from a survey telescope doing its nightly rounds. In the dry air above Rio Hurtado, Chile, one of the Atlas telescopes, part of the NASA-funded Asteroid Terrestrial Impact Last Alert system, run by the University of Hawaii, snapped a routine set of sky images on July 1st, 2025. Software compared those frames against the fixed star field and flagged a faint speck that moved just enough to matter. In minutes, that moving dot became a candidate on astronomers' radar. Something new, something fast. By dawn in Chile, the sighting had a temporary code, 11PL3Z, and a place on the Minor Planet Center's Near-Earth Object Confirmation page, the global bulletin board where possible new things wait for backup eyes. That code is deliberately ugly. It's not meant for poetry, just to rally telescopes. Observers jumped. With a fresh sprinkling of measurements, positions from different places on Earth, the object's path began to sharpen. The track didn't look like a normal bound comet loop. It looked like a drive-by. Within a day, dynamicists crunching the new arc realized the orbit wasn't closed. It was an escape path. The next morning, July 2nd, the Minor Planet Center issued its formal circular and changed everything. The candidate became an interstellar comet. In officialese it read, 3I Atlas equals C/2025-1 Atlas. In plain language, third interstellar visitor ever found, discovered by ATL-AS. The follow-up blitz answered the what is it question almost as fast as the where is it going. 1. Early images hinted at a faint haze around the nucleus, a tiny atmosphere of dust and gas that only comets wear when sunlight warms their ices. That made it unlike the first interstellar visitor Oumuamua, which never sprouted a visible coma. Reporters called, telescopes pivoted, and by late July even Hubble had pointed in and captured that classic teardrop blur cocooning the core. The verdict was in, this wasn't a bare rock, it was a living comet from somewhere else. Here's how the names stack up and why they matter. The 3 in 3I Atlas is a counter. It's the third interstellar object recognized since we started keeping score. After 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The I is a special tag the International Astronomical Union created for interstellar visitors once Oumuamua broke the system. Before 2017, there wasn't a neat way to file outsiders. In parallel, because this object clearly behaves like a comet, it also got a standard comet designation, C/2025N1 Atlas. C/ marks a non-periodic comet. 2025 is the year of discovery. N1 tells you it was the first comet announced in that mid-year half-month slot, and Atlas credits the survey that found it. Put simply, the 3i label tells you what kind of thing it is, the C/2025 and 1 tag tells you how and when it entered the comet catalogue, and Atlas honours the discoverer. The discovery story didn't end with the press release. Once astronomers know a new object's rough track, they comb old images to see if it was hiding there all along. That pre-covery detective work stretches the timeline backwards, tightening the orbit and revealing behaviour before anyone was looking. For 3i Atlas, NASA's test spacecraft had already stared at the right patch of sky in May and early June 2025. When researchers went back and stack-searched those frames, the interstellar comet popped out, faint but real, and may have been active even out beyond the orbit of Jupiter. Around the same time, data from the Vera C. Rubin Observatory's commissioning images in late June caught it too, days before the official discovery, providing size hints and a better sense of how the coma was growing. Pre-covery turned a one-night wonder into a well-charted traveller. If you're wondering what specifically convinced professionals this was an outsider, it wasn't a single glamorous photo. It was the math baked into those dots of light. As observatories from Chile to Arizona to Hawaii fed in positions, the best fit trajectory refused to close into an ellipse. It described an open, unbound path, moving too fast to be held by the sun for long, exactly what you'd expect from a body flung out of another star system long ago, and only now wandering through ours. Journalists love the speed figure, well over 200,000 kilometers per hour in some reports, but the more important point is simpler. It's not from here, and it's not sort of staying. There's a human side to the naming that's easy to miss. Atlas is both a clever acronym and a promise. The survey's mission is to catch dangerous asteroids early, but along the way it finds the unexpected. By attaching Atlas to C/2025 N1, the system credits the team, the software, the night operators, and the infrastructure that makes nightly vigilance possible. And by awarding the interstellar 3i number, the Minor Planet Center places the discovery in a tiny historic sequence, one that started with Oumuamua and will, thanks to next-generation surveys, likely grow a lot faster in the 2030s. From a storytelling perspective, the timeline is satisfying because it compresses centuries of skywatching into 36 hours of modern teamwork. Night 0, Atlas. Chile spots a fast mover and pings the world. Hours later, follow-up telescopes extend the arc and see a whisper of coma. Morning after, the MPC stamps 3i Atlas and C/2025 N1 Atlas on the books, and the hunt for pre-covery begins. Days later, a Hubble portrait confirms the cometary shroud. Each step adds a layer. First motion, then nature, then identity, until the stranger has a proper place in our catalogues and our imaginations. What makes this chapter more than a footnote is what those names unlock. The interstellar tag fuels international observing campaigns in telescope time. The comet designation cues up the chemistry playbook, spectra, dust models, gas species, and the Discover credit helps fund the very surveys that will net the next one. The process is bureaucratic on the surface, but it's really a passport, one that lets a snowdark traveller from another sun move through the checkpoints of our scientific system so the whole world can study it before it's gone. And for anyone watching at home, that first day is a perfect microcosm of how discovery actually works now. Humans and algorithms scouting the sky together, a global switchboard that routes promising finds to fresh eyes, and a naming system that, in a few crisp letters, tells the story of origin, nature, and credit. 3i Atlas didn't just arrive. It was noticed, confirmed, and named in a way that will make everything we learn from it easy to find, test, and build on. That's how a faint smudge becomes a headline, and a headline becomes history. Picture the scene from our side of the sky. 3I Atlas slides into the sun's glare just as it reaches its moment of maximum drama. Closest to the sun doesn't mean skimming the photosphere, it means threading the outer lanes of the inner solar system about 1.5 times farther out than we are, then slingshotting away forever. The calendar is tight. Solar conjunction around late October hides it from backyard eyes, and then, right on cue, perihelion lands around October the 29th to 30th, 2025 at roughly 1.4 astronomical units from the sun. That's the week when sunlight pumps the most energy into its surface when ices simmer, dust lifts, and the coma and tail do their show. We'll miss most of this with ground telescopes because the sun sits in the way, but space-based eyes and careful planning pick up the slack. If you're imagining a flaming snowball, dial it back, the comet is far, faint and safe. Closest to the sun this time is still outside Earth's path and inside Mars's. Closest to Earth doesn't arrive until mid-December, and even then it's a clean miss at about 1.8 astronomical units, hundreds of millions of kilometres away. So the week of perihelion is not a doomsday clock, it's a science clock measuring how a visitor from another star behaves under a stronger dose of sunlight. What actually happens to 3I Atlas during those days? The same physics that drives any active comet, just written in an interstellar accent. As the nucleus warms, gases trapped in the ice escape, dragging dust into a hazy envelope and tail. Hubble already caught that teardrop shroud back in July, and images in late August showed the tail lengthening as activity ramped up, so perihelion week is when those processes crest. The coma becomes the lab note we can read. Its light tells us what molecules are present and how they change as the comet rounds the bend. Because Earth is blinded by the sun then, the baton passes to spacecraft that can watch near the solar line of sight. Solar observatories and heliophysics missions, SOHO, Solar Orbiter, even Parker Solar Probe, are expected to have the comet wander through their fields of view in late September through mid-November, offering intermittent checks on its activity when we can't see it from the ground. Even weather satellites can sometimes glimpse objects close to the sun. During conjunction windows, some instruments may record a faint moving puff with a tail where amateur telescopes can't. It's not a continuous movie, but it's enough to track whether activity spikes or settles as perihelion ticks by. Elsewhere in the solar system, a lot quietly unfolds. Earlier in the month, October the 3rd, 3I Atlas brushed past Mars on the outside lane, close enough that orbiters there had a chance to try for measurements. That proximity set up a rolling handoff. Mars missions near the start of October, solar missions through the hidden week, and then other spacecraft picking it up later as geometry improves. It's a relay race designed by celestial mechanics, not by us. While observers on Earth wait out the glare, plans for reacquisition are already set. Most forecasts agree. As November opens, elongation from the sun grows day by day, and the comet should creep back into the pre-dawn sky, very low and still faint before becoming easier to monitor later in the month and into early December. It won't be a naked eye spectacle, projections keep its brightness in the telescopic range, but for scientists, easy to see isn't the goal. Repeatable spectra and steady imaging are, and those become practical again once the sun steps aside. If you like clean timelines, the week frames itself neatly. Just before the turn, conjunction means invisible to us. In the middle, perihelion, maximum heating and maximum chance for subtle changes like jets, outflow rates and tail structure. Just after, a slow fade from peak activity as the comet heads outward, with visibility from Earth recovering and the first post-perihelion spectra rolling in. Think of it as a 3-act play squeezed into 10 days. Hide, heat, reappear. A few signposts help anchor the bigger picture beyond that week. On November 3rd, 3I Atlas passes Venus at a respectful distance, another non-event for safety, but a nice marker on the outbound track. On December 19th, it makes its not at all close closest to Earth, still nearly twice as far as the Sun is from us, and in March 2026, it sweeps past Jupiter's neighbourhood, again not a collision course, but close enough that missions in the Jovian system could sniff changes in the solar wind or dust environment. Each waypoint is a chance to add a puzzle piece to the brief portrait we're building. For anyone wondering what to expect visually as it re-enters the morning sky, patience and modest expectations. Even at its best, 3i Atlas is not forecast to dazzle casual skywatchers, but the cameras and spectrographs that matter don't need dazzle, they need access. Once the comet is clear of the sun, coordinated campaigns will resume from large observatories and dedicated survey scopes, comparing before and after perihelion data to see if the activity profile changed, if the dust grain sizes shifted, or if certain gases peaked and waned. Those are the quiet clues that turn a fleeting visitor into a lasting insight. So that's the week in plain terms. Not a sky-filling comet head, not a threat to Earth, just a precious, partially hidden peak in the light curve of an object from somewhere else. During those days, 3i Atlas and the Sun write their closest chapter together, while we listen from the wings, then step back on stage in November to read what was written. And even if most of the action happens off camera for us, the recorders are rolling, and the data from that hot, brief pass will ripple through our understanding long after the comet is a dim smudge heading for the dark. What makes 3i Atlas so fascinating is the paradox at its heart. It behaves like a familiar dust and ice comet, yet plainly doesn't belong here. It was found by a hazard hunting survey, logged in our catalogues like any newcomer, and then immediately started acting like a messenger from somewhere else, kicking off real, observable chemistry while racing through on a one-time visit. If Oumuamua was the quiet, puzzling stranger and Borisov the textbook comet from another star, 3i Atlas is the charismatic outlier in between, active, complex, and full of clues. The earliest sharp portraits set the tone. Hubble's July images revealed a classic teardrop haze, dust and gas enveloping a nucleus you can't see directly, plus a sun-warmed plume on the daylit side. From those data, astronomers constrained the nucleus to be no larger than a few kilometers across, with a wide lower bound still possible, and noted that this interstellar visitor is tearing through space faster than any comet we've recorded. That combination, clear cometary behaviour and an unbound high-speed path, announces that we're not just seeing a comet, we're seeing a comet from somewhere else's nursery. Then came the first taste of its chemistry, and that's where the weird really starts to sing. Using the James Webb Space Telescope, researchers picked out unmistakable fingerprints of carbon dioxide dominating the gas, alongside water, carbon monoxide, water ice, and dust, plus a clear say symmetry, with outgassing stronger on the sunward side. The measured CO2 relative to H2O appears unusually high compared with most comets we've studied, hinting that 3i Atlas either formed in a CO2-rich zone of its home disk, or that its surface layers respond to sunlight in a different way than typical solar system comets. In simple terms, the recipe looks skewed, and that skew tells a story about the kitchen it came from. Even before it got close, 3i Atlas pulled off another surprise, water showing up early. Ultraviolet observations detected OH, a standard byproduct of water, when the comet was still way out beyond where water usually wakes up efficiently. That suggests an unusually active surface, or that big icy grains lofted off the nucleus were carrying their own water supply, releasing it as they floated outward. Either way, it's not the wait until you're warmed up behaviour we expect. It's more like a traveller unzipping the suitcase while still on the moving walkway. Then there's the geometry of its dust, strange and beautiful. Multiple datasets show a feature extending toward the sun, the opposite of a normal tail. This so-called anti-tail or sunward jet isn't just a camera trick. Analyses argue it's driven by the way sunlight sculpts which grains survive, how fast they loft, and how long they last in different directions. The result is an elongated, sun-facing structure layered on top of the usual tail that streams away from the sun. We've seen anti-tails before in solar system comets due to perspective, but the early persistent sunward structure in 3i Atlas looks like a genuine physical plume, not a simple viewing effect. That's unusual and scientifically delicious because it lets us probe grain sizes, lifetimes and outflow patterns in a brand new environment. Its light does another strange thing. Polarimetry, the way scattered light gets subtly oriented, shows 3i Atlas has a deep, narrow, negative polarization at small Sun-comet observer angles, a combination not seen in ordinary comets and even distinct from 2I/Borisov. That points to a different mix or texture of grains in the coma, possibly a blend of brighter ices and darker carbon-rich material arranged in a way that flips the usual scattering signature. It's an esoteric measurement with a simple takeaway. The dust floating around this object doesn't behave like the dust we're used to, which again circles back to different formation or processing conditions around another star. Meanwhile, the wonderful half of the story is how quickly the picture is sharpening. As 3i Atlas drew inward through August and early September, Gemini South caught the tail growing and the coma broadening. Plain evidence that the heat is dialing up activity as expected, but with its own interstellar accent. Those images feed models of dust production rates and grain sizes, and they anchor a timeline so we can compare before perihelion to after perihelion without guessing. All of this lands differently because we've only had 2 interstellar points of comparison. Oumuamua never sprouted a visible coma and confounded us with a subtle, non-gravitational push. Borisov, by contrast, looked and behaved like a garden-variety comet with some compositional quirks. 3i Atlas is blazing a third trail, a clearly active comet that nevertheless departs from the norm in its sunward plume, its polarization signature, and its CO2 heavy breath. The more ways it defies expectation, the more precisely we can sketch where and how it was made. If you're crafting visuals or narration, lean into those contrasts. Show the Hubble cocoon and sunward plume as the "this is alive" moment. Then reveal the Webb spectrum story as a colour-coded bar graph, lots of CO2, less water than expected, and translate that into a map of a distant protoplanetary disk, where 3i Atlas may have frozen together, closer to the CO2 line than our comets typically do. Use the anti-tail as your "what on earth?" well, what in space is that hook, and explain it with a simple idea. In some directions, grains last longer and pile up differently, so the comet wears a little forward scarf as well as a trailing train. Wrap with the polarimetry as the forensic dust test. The light itself says the grains are different. That's why this visitor matters. 3i Atlas isn't just a headline about a fast rock from afar. It's a working lab on a hyperbolic fly-through, letting us sample chemistry, dust physics, and sunlight-driven activity from a star system we'll never reach. Every oddity, its CO2-rich breath, its sunward plume, its quirky polarized light, adds a brush stroke to the first comparative portrait of comets across the galaxy. And in that portrait, weird is exactly what we need to learn something new. Think of 3i Atlas as a memory core wandering between suns. Most comets are local, frozen leftovers from our own system's construction site. This one was built around another star, then thrown into interstellar space and left to drift for ages before arriving here. That's why scientists call objects like this time capsules. Their ices and dust hold the chemistry of a distant protoplanetary disk, preserved in cold storage. Studying what boils off and what kind of dust it sheds lets us read the conditions of its birthplace. How hot or cold it was, how much carbon, oxygen, and other elements were available, and how material was mixed as planets grew there. With only 2 earlier interstellar visitors to compare, Oumuamua, quiet, no visible coma, and 2I/Borisov, a very active, textbook comet, 3i Atlas gives us the first real chance to start seeing patterns instead of one-off curiosities. The most electric clues come from light split into its ingredients, spectroscopy. Point a sensitive spectrograph at the faint glow of the coma and you can tell which gases are there from their unique barcodes. Early space-based results already show that 3I Atlas is venting water and carbon monoxide, but with carbon dioxide standing out in an unusually strong way. That skew matters. A CO2-rich breath hints the object froze together in a cooler, CO2-friendly zone of its original disk, or that its surface layers are arranged so carbon dioxide escapes more readily than water as sunlight warms it. Either way, the ratio itself is a fingerprint from another solar system's chemistry, now readable as the comet wakes up. Dust carries a different kind of memory, the texture and makeup of the grains that built worlds. When sunlight scatters off those grains, the light's polarization changes in subtle, measurable ways that depend on grain size, porosity, and composition. For 3I Atlas, polarimetric campaigns have reported an unusually deep negative polarization at small sun angles, a combination not seen in ordinary comets, and even distinct from 2I/Borisov. The simple takeaway, the dust here isn't behaving like the dust we're used to. That points to a different recipe or processing history, perhaps fluffier, more porous grains, or a distinctive blend of bright ices and darker carbon-rich material. Each of those possibilities maps to different conditions in its birth disk. The time capsule label isn't just about what's in the coma today, it's also about how the object has changed on the way in. Thanks to pre-covery work, digging into images taken before discovery, researchers pulled 3I Atlas out of months-old test data, extending its brightness record back into late spring. That longer timeline makes it possible to see when activity first switched on, how fast it ramped, and whether there were fits and starts. The more of the story we can stitch together before and after its closest pass to the Sun, the better we can separate universal comet behaviour from quirks that belong to this one alien traveller. Interstellar comets also let us test big ideas about how disks are layered and mixed. In our own backyard, 2I/Borisov stunned astronomers by carrying far more carbon monoxide than water near the Sun, already a hint that other systems park their ices differently than we do. 3I Atlas adds another data point with its CO2-heavy signature. One object can always be an oddball. 2 and 3 begin to outline the range of what normal looks like across other suns. Those ranges then feed the models that predict which planetary systems end up rich in volatiles, the raw stuff of atmospheres and oceans, and which do not. If we can go deeper than which molecules, we touch the real treasure: isotopes, nature's tiny tags. Ratios like deuterium to hydrogen D/H in water, or different flavours of carbon and oxygen, act like thermometers and timestamps for where and how ice is formed. In comets from our own system, those ratios have been used to argue about where Earth's water came from and how the young sun's disk stirred and evolved. Measuring such ratios in 3I Atlas, if it's bright and clean enough, would be a landmark, because it would let us compare not just ingredients, but the precise conditions of 2 different planetary nurseries. Even if the measurements prove challenging this time, the roadmap is clear. Every future interstellar comet is a chance to read the isotopic handwriting of another star. The dust's geometry can add footnotes to the story. High-resolution Hubble imaging of 3I Atlas has shown dust flowing from the sunward side of the nucleus even far from the Sun, a sign of steady sunlight-driven activity, while ground-based work has reported odd, sun-facing features at times. The detailed physics behind such structures, jets, anti-tails, or viewing angle effects, matters because it constrains the grain sizes and how easily they're lofted. Those parameters tie back to the comet's mechanical makeup, how loosely the grains are bound, how crumbly or compact the surface is, which in turn reflects how it was built. A different disk can build different bricks. 3 visitors in 8 years might feel like a trend, but scientifically we're still data poor. That's about to change. The Rubin Observatory's decade-long sky movie is expected to turn up interstellar visitors far more often, with conservative studies pointing to roughly a dozen plus over 10 years, and some analyses allowing for much higher rates depending on the true abundance and reflectivity of the population. More interstellar comets mean statistics instead of anecdotes, enough to map out the diversity of extrasolar ices, dust textures, and activity styles, and enough lead time to coordinate space-based observations, or someday rapid response flybys, that catch them at their most revealing. And that's what could change everything really means here. Not catastrophe, clarity. A single interstellar comet can tweak our models, a handful can redraw them. With 3I Atlas, we're already seeing chemistry and dust behaviour that don't line up neatly with our local experience. As more of these time capsules arrive and we assemble their chemical passports, we'll learn which parts of planet building are universal and which are idiosyncratic. We'll better predict which stars are likely to host ocean worlds or dry, airless rocks. We'll refine where to point our biggest telescopes in the search for habitable atmospheres. The messenger from another sun is fleeting, but the message, written in ice, dust and light, could echo through everything we think we know about how worlds are made. If you're thinking, we can't possibly send a new spacecraft after this thing in time, no, you're right. And that's exactly why the existing fleet becomes the sneaky superpower in this story. 3I Atlas is threading paths that line up with probes we've already got all over the inner solar system, turning routine missions into opportunistic observatories. The upshot is a relay of vantage points. A few caught it on the way in. Some can watch during the sun-blinded weeks around closest approach, and others may sniff its wake afterward. The first handoff came earlier than most people noticed. NASA's Psyche spacecraft, en route to the metal-rich asteroid of the same name, passed within a few tenths of an astronomical unit of 3I Atlas in early September. A recent study mapped out that geometry and argued Psyche could contribute valuable phase angle snapshots of the coma, how the comet's glow changes, with Sun-Comet observer angle. There are caveats. Psyche is often thrusting, so pausing for long steady images can be tricky. Still, even short sequences help fill in how the comet's dust scatters light from a new angle in space. Think of Psyche as the early scout on the inbound leg. Then Mars got front row seats. On October the 3rd, as 3I Atlas swung by the red planet's orbit, ESA turned two of its workhorse orbiters, ExoMars Trace Gas Orbiter and Mars Express, toward the visitor. ExoMars Cassis camera captured it as a soft-moving dot with a clear coma. Mars Express also tried imaging and spectroscopy, with teams stacking frames to dredge out signal. The distance was still tens of millions of kilometres, so nobody expected dramatic pictures of the nucleus. But even these faint views are precious, because they pin down the comet's brightness and activity trend right before the sun hides it from Earth. And they prove the concept, repurpose flight-tested orbiters for quick, opportunistic comet science when the geometry lines up. The magic of this chapter is what happens while Earth is effectively blind. Around perihelion, 3I Atlas sits close to the sun in our sky, so ground telescopes have to stand down. Spacecraft that stare near the sun don't. A wide-ranging analysis of spacecraft opportunities flags the solar watching fleet, SOHO, STEREOA, and especially Parker Solar Probe with its new ISPR camera, has potential eyes during the very window when we most want updates. If the comet's coma and tail puff up enough, Parker could catch it in white light images from late September through mid-November, tracing changes as outgassing peaks and then settles. It's not guaranteed. Detecting a small point-like comet is harder than imaging broad dust structures. But if any camera can pull off a perihelion week cameo while we're sun-blinded on Earth, it's one of these. Now for the most tantalizing mid-game play, JUICE, ESA's Jupiter Icy Moons Explorer. Just after perihelion, in early November, JUICE enjoys one of the best geometries of the entire campaign. Closer to the comet than Earth and with a cleaner line of sight. Mission planners say they're pointing instruments at 3I Atlas then, with one prize tool in particular, MAJIS, a visible infrared imaging spectrometer designed to map gases and ices. If activity cooperates, MAJIS could look for signatures of water, carbon dioxide, carbon monoxide and other species right after peak heating, exactly when the chemistry is loudest. The catch is timing. Stored data may not downlink immediately during this fast, hot stretch of JUICE's cruise, so we might only see results months later. But scientifically, that window is gold. There's also a clever physics without pictures possibility, catching the comet's ion tail from far away. A new prediction argues that between about October 30th and November 6th, NASA's Europa Clipper spacecraft could sit in just the right place for the solar wind to carry ions peeled off 3I Atlas straight past its sensors. That wouldn't produce a glamour shot, but a sniff of heavy water group ions and related changes in the solar wind would be a direct sample of interstellar material grabbed by a mission that's merely passing through. It's weather dependent in the cosmic sense. If the solar wind streams just right and instruments can be scheduled and averted, Clipper could pick up an ion tail shower. The same modelling flags a shorter window for ESA's Hera probe, though Hera isn't equipped with dedicated in situ plasma sensors. Speaking of Hera, while it's headed to the Didymos system, its instrument deck and the Milani CubeSat it carries focus on imaging, thermal mapping, and tiny dust detection near asteroids, not measuring charged particles in deep space. So even if Hera passes downwind of the comet's tail, it's more likely to contribute context than to record the ion chemistry directly. That said, the mission's cameras and hyperspectral imagers may still snag supportive observations depending on angles and safety constraints. Roll the tape forward and Jupiter's realm becomes the late-game stage. On March 16, 2026, 3I Atlas will pass roughly a third of an astronomical unit from Jupiter, a respectful but scientifically interesting distance. Two threads spin out of this. First, Juno, which has been orbiting Jupiter since 2016, should have decent geometry to monitor the interstellar visitor's environment that month, even without any radical retargeting. Second, and more provocatively, multiple teams have published proposals showing that, in principle, a substantial trajectory change combined with a gravity assist Oberth maneuver at Jupiter could put Juno directly across the comet's path for a true flyby in mid-March 2026. It's daring and would demand fuel, risk, and very careful navigation. It's a concept paper, not a mission plan. But it underlines the theme. Because 3I Atlas brushes Jupiter's neighbourhood, even legacy spacecraft can, in theory, be repurposed to chase brand new science. One more quiet helper arrives late in the act. OSIRIS Apex, the retasked OSIRIS-REx spacecraft now cruising in the inner solar system. As Earth regains a good angle in December, OSIRIS Apex and ground observatories can tag-team follow-up spectra and imaging from different vantage points, adding parallax and cross-calibration as the comet cools. That sort of cross-eye coverage helps separate what's really changing at the comet from what's just a trick of perspective. Pull back and the pattern becomes clear. We didn't launch a bespoke chaser for 3I Atlas, but we didn't need to. Psyche gives us early inbound context. The Mars fleet proves we can redirect multipurpose orbiters on a dime. Solar probes may keep watch during the sun glare blackout. JUICE brings post-perihelion spectroscopy from a sweet spot we can't get from Earth. Europa Clipper might literally taste the ion tail in passing. And Juno, whether simply watching or, in a dream scenario, diving for a flyby, reminds us that long-lived missions can still surprise us with brand new targets. Together, those vantage points turn a brief, unrepeatable encounter into a multi-mission experiment in reading the chemistry and physics of a comet from another star. That's the sneaky opportunity, using the fleet we already have to catch lightning in a bottle. Start with the big picture truth. 3I Atlas is not on a collision course with Earth. Its path through the solar system is an open, one-time arc from deep space that never comes anywhere near to our planet. NASA's current solution puts its closest to the Sun moment around October the 29th to 30th, 2025, at roughly 1.4 times Earth's distance from the Sun, already beyond our orbit, and its closest path to Earth much later, at about 1.8 astronomical units away. That's roughly 270 million kilometres, farther than our distance to the Sun. In short, spectacular science, zero danger. Those numbers aren't marketing, they're geometry measured from thousands of observations. The track is hyperbolic, which means 3i Atlas is flying in from another star and will leave again, unbound. Agencies tracking it have been clear from day one. There is no threat to Earth, with minimum separation comfortably in the hundreds of millions of kilometres. Early mission briefings from NASA and ESA both emphasise this, and they haven't wavered as more data came in. To anchor the timeline, perihelion, its closest point to the Sun, lands near October. 29 to 30, 2025, well outside Earth's orbit. The date people sometimes confuse with Danger Day is December 19th, 2025, which is simply when it's farthest in our direction, about 1.8 astronomical units away. Again, approximately 270 million kilometres. Think of it as passing on a distant outer lane of a racetrack while we're on an inner lane. Our orbits never cross, and the lanes are vastly separated. Why we can be so confident? When astronomers fit an orbit, they also quantify how uncertain that fit is. For 3i Atlas, the uncertainty cloud around the path is tiny compared with the huge gap between it and Earth. Even if you nudge parameters within reasonable bounds, you don't magically steer a visitor hundreds of millions of kilometres off course into us. And while comets can get gentle kicks from jets of gas, outgassing, as they warm, those effects are small compared with the kind of course change you'd need to convert a distant flyby into an impact. The distance margin here isn't a razor's edge, it's a continent. NASA's public updates make the same bottom line point. Closest to Earth is to still about 1.8 astronomical units, no hazard. Another source of anxiety you might see online is the word conjunction. Around perihelion, 3i Atlas sits close to the Sun in our sky, which makes it hard to see from Earth for a couple of weeks. Hard to see is not dangerous. It just means sunlight drowns it out. Spacecraft that look near the Sun, SOHOSTEREO Parker Solar Probe, can keep tabs while ground telescopes wait, and then it reappears in better morning skies in November. The geometry that hides it from our eyes is the same geometry that keeps it far from our planet. If you want extra reassurance, look at how it passes other worlds instead. It skimmed outside Mars's orbit on October the 3rd, close enough for Mars orbiters to snag distant pictures, but still tens of millions of kilometres away. After perihelion, it swings nowhere near Earth, then glides past Venus at a respectful distance, and only much later does it approach Jupiter's neighbourhood on its way out, still on the safe outbound track. The fact that ESA and NASA are using this opportunity for observations, not emergency planning, tells you everything about the risk level. So what should viewers expect as December approaches? A steady drumbeat of science results and a total absence of impact alerts. You may see brightness updates or closest approach to Earth today headlines. Those are routine tracking notes that confirm the same story. The minimum distance is vast. NASA's dedicated page even spells it out in plain language. Closest approach to Earth is about 1.8 astronomical units, and the comet will remain far away the entire time. And if someone asks, could something change at the last minute? You can answer simply and accurately. Orbital solutions are updated continuously as new data arrive, and the numbers keep converging on the same safe outcome. This isn't a guess. It's a well-observed, well-modelled fly-through by a visitor that never enters our lane. The only thing it threatens is our old ideas, because the data it brings may reshape how we think about comets and planet building across the galaxy. Here's the bind we're in. The most interesting chemistry for 3i Atlas happens right as it dives behind the Sun from our point of view. That's solar conjunction, great for waking up the comet, terrible for ground-based telescopes. The way around it is to choreograph a relay of instruments that don't care about glare, then be ready with a second wave the moment it slips back into dark skia, and NASA has already set the calendar beats. Perihelion lands around October 29th to 30th, 2025, at roughly 1.4 astronomical units just inside Mars's orbit. With Earth-based visibility poor through late October/November and improving again in early December when it reappears from behind the Sun. First, we lean on space observatories that stare close to the Sun all the time. SOHO and STEREO have spent decades catching comets lurking in the glare, and Parker Solar Probe's WISPAR camera has even filmed tiny sun grazers skimming the corona, proof that near-Sun imaging works when Earth-based telescopes are blind. Solar Orbiter's Solo-H imager has likewise recorded dramatic comet tails while the spacecraft was practically inside them. During conjunction, those same vantage points can watch 3-eye atlas for outbursts, tail growth, and directional changes we'd otherwise miss. Think of them as our during the blackout cameras. Second, we keep the chemistry tap open with space spectroscopy. Before conjunction, Hubble pinned down the classic teardrop coma and set size limits on the nucleus. JWST then delivered the headline "Surprise," a coma dominated by carbon dioxide with water and carbon monoxide present, an unusually high CO2 to H2O ratio that screams outsider conditions. That means 3-eye atlas is already giving us compositional clues while the geometry is still tricky, and it sets a baseline to compare against as activity peaks around perihelion and fades afterward. Third, we exploit off-Earth viewpoints. In early October, just ahead of conjunction, ESA swung both its Mars orbiters, ExoMars Trace Gas Orbiter and Mars Express, toward the visitor as it passed Mars's orbit, securing faint but valuable measurements right before it slipped into the Sun's glare. Those data anchor the light curve and activity level on the eve of perihelion. After the blackout, other spacecraft farther from our line of sight may have clean shots when we don't. This is the beauty of a solar system-wide network. If Earth can't see, someone else can. Fourth, we plan the reacquisition like a military operation. Once elongation, the angle away from the Sun, grows in early December, big observatories resume work, steady photometry to track how fast the coma relaxes, medium-resolution spectra to look for changes in gas ratios after peak heating, and polarimetry to probe dust textures. NASA's public guidance has been clear. It's hard through September and October, then 3-eye atlas emerges again by early December, so teams have calendars, scripts, and target files ready to go the minute it clears the dawn. Fifth, we set expectations for how to see it. This is not a naked eye spectacle. Even at best, projections keep it in the small telescope range, around the dim double digits in magnitude. That's still perfect for meaningful science. CCD, photometry, low-resolution spectra, and deep imaging to trace faint tails. Amateur and pro networks will stack many short exposures, track at the comet's rate, non-sidereal tracking, and subtract stars to tease out delicate structures. Guides for moving target tracking and comet observing used at Gemini, Keck, the BAA and elsewhere give observers a playbook for low-contrast twilight work and bright time data. Sixth, we put the citizen science army to work. Networks like COBS, the Comet Observation Database, the SkyLive Planners, and Unistellar campaigns make it easy to coordinate thousands of small telescopes, share ephemeroids, and push real-time updates on brightness and morphology. In July and August, backyard observers and smartscope owners already snagged images. As 3-eye atlas returns to the morning sky, those same groups will log magnitudes, coma diameters, and tail position angles, bread and butter data that complement the big facilities. Seventh, we try non-visual tricks while the comet is hard to see. Radio and millimeter arrays like ALMA can sniff specific molecules where an optical telescopes struggle, and this technique is well proven on other comets, mapping gases such as HCN and formaldehyde, and even tracking outflows in 3D. If scheduling and brightness cooperate, sub-mm snapshots near and after perihelion can check whether the CO2-rich personality from JWST is mirrored by other species that light up at longer wavelengths. Eighth, we stay opportunistic with heliophysics missions. When a comet's ion tail gets swept into the solar wind, in situ instruments can taste its ions from far away. Solar Orbiter has literally flown through comet tails, Parker and other craft can watch how the solar wind sculpts 3I Atlas's plasma environment. Even if no glossy image appears, a wiggle in ion counts is science gold, a remote sampling of matter from another star system hitchhiking on the wind. Ninth, we keep the public scoreboard honest. NASA's 3I page tracks the key facts, perihelion timing, distances, and the simple reminder that this body is far and safe, while ESA posts mission-by-mission updates like the Mars orbit observations. For night-to-night practical planning, community hubs like COBS and the Sky Live display updated ephemerides, elongation, and altitude for your location. That mix, official sources for the geometry, community tools for the when and where, is how we move through a fast-changing observing season without getting lost. Finally, we use what we learn to make the next one easier. Rubin Observatory's survey will be superb at flagging faint, fast movers once it's fully on sky. SOHO, STEREO, and Solar Orbiter have shown how to bridge conjunctions. JWST proved that interstellar comets can be chemically profiled even when they're far from the Sun. Together, those lessons turn an awkward geometry into a template. When the next messenger arrives, the relay is already rehearsed. Spacecraft cover the blackout, citizen networks fill gaps, and the big guns pounce the instant it clears the Sun. 3I Atlas is the stress test, and beating it means we'll never waste another interstellar visitor to timing again. Every time a stranger from another star shows up, the same whispers rise. What if it isn't just a rock? The question is fair and powerful, because it forces science to show it's working. With 3I Atlas, the process begins from the most boring, disciplined place on purpose. Assume it's natural, then try as hard as you can to break that assumption. You look for behaviours that nature struggles to explain. Steady radio transmissions that drift like a transmitter. Light curves that imply engineered shapes. Accelerations that don't match outgassing. Glints like specular reflections. Unusual spectra that scream metal and paint instead of ice and dust. If any of that appears, the conversation changes. If it doesn't, the alien probe idea stays on the shelf, fun to imagine but unsupported. We've been here before. In 2017, Oumuamua arrived. Looked like no comet we'd ever seen. And then, most controversially, sped up in a way gravity alone couldn't explain. That mystery was oxygen for speculation. Over the next few years, teams revisited every scrap of data. A 2018 analysis measured the extra push with high confidence. Later work showed you could get that gentle acceleration if trapped hydrogen bubbled out of processed water ice as the object warmed. No thrusters required. Breakthrough. LISTEN pointed the Green Bank telescope at it, scanned across multiple radio bands, and heard nothing artificial. The upshot wasn't no aliens exist, just that the evidence on the table fit a natural object better than a craft. That's the template. Test the weirdness until it turns ordinary, or until it won't. The second visitor, 2I/Borisov, calmed the waters. It behaved like a classic comet with some striking chemistry, unusually rich in carbon monoxide compared to many local comets, yet still plainly natural. SETI teams listened there too. Again, no techno-signatures. That case reminded everyone that different from us doesn't mean built by someone. It means the kitchen it came from stocked its shelves in a different way. So where does that leave the newcomer? 3I Atlas is visibly active. Coma and tail, the whole cometary ensemble, on a hyperbolic path that never binds to the Sun. NASA's fact sheet is blunt. It's an interstellar comet, not a threat. And its closest path to Earth is still roughly 1.8 astronomical units away. Nothing about that baseline screams engineered. If anything, it slots neatly into the natural but valuable category. A time capsule from another planetary nursery we can read as sunlight shakes its chemistry loose. Still, big claims deserve big tests, and 3I Atlas will get them. What would count as suspicious? Start with motion. Astronomers compute an orbit from hundreds of precise positions. If there's a persistent, non-gravitational shove that can't be explained by sun-warmed ices venting gas, and that shove doesn't line up with any plausible jets, eyebrows go up. That's the same kind of anomaly that made Oumuamua a riddle before hydrogen outgassing made the numbers work. With 3I Atlas, we already see normal comet behaviour, which means any extra acceleration can be modelled by jets without invoking engines. If the residuals drop towards zero as their models include activity, the probe hypothesis loses oxygen fast. Next, the communication check. When new interstellar visitors show up, radio arrays sometimes run targeted listens for narrowband drifting tones, exactly the kind of signals nature almost never produces, but transmitters do. Breakthrough Listen pioneered this play during Oumuamua and repeated it for 2I/Borisov. The 2025 literature even lays out how to scale that strategy for future interstellar arrivals as Rubin Observatory finds more of them. If a similar campaign points dishes at 3I Atlas and hears a steady structured signal that follows the object across the sky, that would be headline changing. So far for Oumuamua and Borisov, the result has been silence. Silence isn't proof of absence, but it's not evidence of presence either. There are other subtle flags people look for. Artificial surfaces can glint in telltale ways. Engineered objects can tumble with strangely regular light curves. Metal-rich spectra can give away alloys instead of minerals. Coherent flashes might mimic beacons. In practice, 3I Atlas is faint, distant, and wrapped in dust and gas, exactly the conditions that hide any surface details and make radar or high-res imaging unrealistic at these ranges. That's why the community leans on spectra, what gases and solids are present, and dynamics, how it moves, rather than glossy close-ups. If those two pillars look normal, the conservative conclusion stands. This isn't just about one comet. Over the last few years, NASA and the broader technosignatures community sketched a responsible framework for testing extraordinary ideas without turning science into a circus. It boils down to define the signals you're looking for, publish your methods in advance, archive the data, and invite independent teams to try to break your conclusions. That playbook grew out of workshops and white papers and now guides how Could It Be a Probe gets translated into actual telescope time, search algorithms, and public results. You can already see the pattern with interstellar objects: fast alerts, coordinated listens, sober null results when nothing weird turns up, and careful papers when a natural explanation fits best. If you want to give your audience a truth they can carry, offer this. Skepticism isn't cynicism, it's quality control. The reason the alien probe idea stays on the table as a possibility, rather than becoming a punchline, is precisely because scientists refuse to wave it away or embrace it without evidence. Oumuamua's mystery pushed researchers to invent better models of outgassing and ice processing. Borisov's richness in carbon monoxide rewrote expectations for extrasolar chemistry. 3I Atlas is already sharpening how we schedule listening campaigns, how we model non-gravitational forces, and how we compare comet dust across star systems. The debate makes us better, even when the answer is natural. So, what would it actually take for 3I Atlas to change everything in this debate? Something unambiguous. A narrowband transmission that turns on and off with the comet at a frequency and drift matching its motion, confirmed by multiple observatories. A maneuver, an abrupt, sustained change in its path that can't be chalked up to jets, with timing that looks intentional. A spectrum with signatures of refined alloys or manufactured polymers. A repeating optical flash with a pattern that screams code, not sunlight. Any one of those would flip the script from probably natural to we need to rewrite the chapter. Short of that, the smartest bet is the boring one. 3I Atlas is a natural interstellar comet that we can study to learn about worlds we'll never reach. That's already astonishing enough. And if someone insists the scientific community is biased against exciting answers, point to the record. When a claim fits the data better than the alternatives, it wins, no matter how surprising. The reason Oumuamua isn't filed under Alien Probe today is that a physically grounded, testable natural model explains its odd push without special pleading, and every targeted search for a transmission came up empty. The reason 3i Atlas isn't getting the same swirl of speculation is simpler still. It looks, moves, and breathes like a comet. Until the evidence says otherwise, that's exactly what it is. An emissary of another sun, not a spacecraft, but a messenger whose story will keep shaping how we look and listen the next time a stranger arrives. If there's a moment where a single icy stranger can quietly tilt the course of science, this is it. 3i Atlas doesn't rewrite our world with spectacle, it rewrites our playbook with clarity. First, it forces a new standard for interstellar readiness. Until now, we've treated each visitor like a one-off miracle. After this, the community will behave as if there's always another on the way. Pre-approved observing plans sitting in desk drawers, time on big telescopes held in rapid response queues, and spacecraft teams keeping a standing checklist for point now, ask later. The choreography we improvised this time, handing the baton from ground observatories to solar probes during conjunction, then back again, becomes an official routine. Proposal templates will change, data pipelines will change, the posture of the field will change from reactive to poised. The second shift is the map we're building. With 3i Atlas, we're beginning a chemical atlas of other solar systems, compiled comet by comet. It's not just what molecules anymore, it's where those molecules make sense in a disk, what temperatures they imply, how dust grains are stitched together. Give this effort 10 interstellar comets and the picture gets startlingly specific. Which star-forming regions tend to produce CO2, heavy bodies? How common carbon-rich dust really is, whether the recipes that build ocean worlds are rare, ordinary, or everywhere. That map loops back into exoplanet science. When a telescope sniffs an atmosphere around a distant world, we'll have better priors for what raw materials existed there in the first place. The silent chemistry of 3i Atlas becomes a loud voice in debates about habitability. Third, missions themselves will be designed differently. The idea of a prepositioned interceptor parked near Earth, fueled, sensors warmed, waiting for a target, stops sounding extravagant and starts sounding obvious. So does a small, fast, many approach. A clutch of nimble probes that can be retasked on short notice, each good at one thing, snapshots, infrared, spectra, dust sampling, and launched on commercial rockets in weeks, not years. The stress test with 3i Atlas shows where the friction is. Pointing constraints, software that isn't built for moving targets, thermal limits near the sun. Solve those and the next object could get not just spectra but close-range imaging, maybe even fly-through dust sampling. The dream of a true intercept goes from someday to when the detection comes early enough. Fourth, detection will come earlier. Survey cadence, automation, and coordination are already leaping forward. After 3i Atlas, pipelines that flag too fast, too weird trajectories will page the right people instantly, not tomorrow. Citizen sky networks will have shared dashboards ready to push ephemeridism to backyard telescopes worldwide. Space agencies will maintain cross-mission alerts, so a geometry sweet spot for one spacecraft doesn't slip by unnoticed. The same machine learning tools we use to spot asteroids will be tuned to whisper, "This one's an outsider," days sooner. That extra time is everything, time to point, to plan, to learn. Fifth, the data culture changes. 3i Atlas has been a masterclass in open, rolling science. Preprints posted as spectra arrive, raw images released for others to reprocess, amateurs contributing photometry that pros fold into models. Expect this to harden into a norm. Interstellar mode will mean a public data room, calibrated images, reduction scripts, live brightness thumb curves, so anyone from a major observatory to a classroom can test hypotheses in near real time. The more eyes, the fewer blind spots, The fewer blind spots, the faster we discover what truly doesn't fit. Sixth, the physics of dust and ice gets a reality check. The sunward plume, the polarization quirks, the unusual gas mix, details like these nudge our models out of comfort zones. If grains survive longer facing the sun than we thought, if CO2 dominates in regimes where we expected water, then our lab experiments and computer simulations need retuning. That ripples into everything from how we model early planet formation to how we estimate the durability of cometary material when it brushes close to a star. It also reframes the origin stories of our own comets. Were we ever looking at the full spectrum of possibilities, or just the local dialect? Seventh, we get braver about the long shots. Isotopic fingerprints are hard to measure on a faint, fast traveller, but 3i Atlas has made the community hungrier to try. Expect more campaigns aimed squarely at those tiny ratios, the subtle tags that tell you where and when ice is formed. Even a single solid measurement from an interstellar comet would be a landmark, a number that says, their nursery ran colder or hotter than ours. If not this time, then next time, because now we know exactly what to look for and how to organise the hunt. Eighth, public imagination gets invited in the right way. 3i Atlas is a hazard to misconceptions, not to Earth. Explaining why, clear diagrams, clean distances, the difference between closest to the sun and closest to us, builds trust that will matter when the next object arrives. And because the most dramatic science often happens while the comet is hidden in glare, people learn that discovery isn't a fireworks show. It's a relay of instruments listening in wavelengths our eyes can't see. That's a deeper kind of wonder, and it keeps attention where it helps, on the data, not the doom. Ninth, the argument about are we alone gets healthier. The responsible way to treat the alien probe idea isn't to scoff or to swoon, it's to measure. 3i Atlas pushes that culture forward. Define the telltale signs, run the listening campaigns, publish the null results, and let natural explanations stand when they fit best. Each well-run search calibrates our expectations and improves our tools. If something unambiguous ever does appear, a deliberate signal, an impossible maneuver, we'll catch it because we got good at catching everything else. Finally, humility gets sharper edges. 3i Atlas is a postcard from a place we'll never visit, yet its dust now drifts through our instruments. Its gases write bright lines in our spectra. Its path bends through our maps. We are learning that the galaxy shares. It throws us samples if we are quick enough, organised enough, open enough to read them. The real change then is not just in our models or our missions, but in our reflexes. From wow, what luck to we're ready. When the next messenger appears, and it will, our instruments will already be listening. Our proposals already cleared, our small craft already warmed. And somewhere, as that new traveller sheds its first whisper of alien frost into sunlight, someone will look up and think, not we might miss this, but we know exactly what to do. When a stranger leaves your town, you suddenly notice what it taught you by just passing through. That's where we are tonight. 3i Atlas came in quiet, flared to life in the sun's glow, and now slips back into the dark with a soft cometary exhale. No drama, no danger, just a one-time conversation in ice and light that left us a little less certain and a lot more awake. We set out chasing a headline and found a mirror. 3i Atlas is not from here, yet its story rhymes with ours. A nursery of dust and gas, a long wandering childhood, a chance encounter with warming light, and then the road again. It reminded us that the galaxy isn't a scatter of isolated islands, it's an ocean with currents, trading little memory cores between shores. Every molecule it released, every grain of dust it carried, was a postcard from another star's beginning. If this journey cracks something open for you, let it be this. Wonder and rigour can live in the same heart. It's okay to feel the goosebumps while the spectra roll in. It's okay to be moved by a smear of light on a sensor, because you know what it means. A chemistry lesson from a place we'll never visit. We didn't need to conjure fear or fantasy to make this story big. We just had to listen carefully, test ideas honestly, and let the cosmos be strange on its own terms. What actually changed? More than a news cycle. 3i Atlas made us faster. It forced telescopes to move together like a single organism, handing the baton from Earth to spacecraft during the glare, then back again as the dawn opened. It made old missions feel new. Orbiters, solar probes and cruisers turned into opportunistic comet hunters, catching a visitor we didn't plan for but were ready to meet. It sharpened our questions. Why so much carbon dioxide here? Why that sunward plume? Why that peculiar dust signature? It's not that we found every answer, it's that we learned exactly which answers are worth losing sleep over. And we learned something about ourselves. For all our noise, we are a patient species when the universe asks us to be. We'll stack the faintest images, sift the thinnest lines in a spectrum, and wait weeks for a better angle just to squeeze one more clue from a quiet traveller. That patience is power. It's how a dim smudge turns into knowledge that can outlast headlines, outlast us. As 3i Atlas fades, I want to leave you with a few invitations. First, take this outside. The next clear morning, step into the cold air and look east, even if you can't see a comet. Notice how many bright things are moving. Planets drift, satellites blink. The sky is a live system, not a postcard. That shift from picture to process is the secret door into astronomy. Once you feel it, every point of light becomes a story in motion. Second, add your voice to the record. Maybe you run a backyard telescope and can contribute a magnitude or two. Maybe you sketch what you see. Maybe you write a poem about a messenger that will never return. It all matters. Shared curiosity is how we build a culture that funds the next instrument, trains the next observer, and keeps the lights on for the long watches when the sky's stingy. Third, carry the calm. The internet loves a good panic. We don't. 3i Atlas was far and safe and beautiful. Most of the universe is like that, distant and generous. When the next object appears, and it will, be the person who brings clarity to the group chat. Distances, dates, what matters, what doesn't. You'll be surprised how many people are waiting for someone to steady the lens. Finally, keep the door open to surprise. We asked the big, wild questions too. Could it be technology? Could it be a beacon? And then we did the work. The best part of science isn't a dramatic yes or no. It's learning to recognise a trustworthy probably, and to upgrade it when the evidence changes. 3i Atlas trained that muscle. If something truly astonishing arrives one day, we'll catch it not because we were shouting, but because we were ready. So here's how we close. Somewhere far beyond our maps, a tiny nucleus is cooling, its short season in sunlight already a memory. Behind it trails a faint, dissolving script of dust that only instruments will ever read. And we did read it. We turned a chance flyby into a shared lesson about how worlds begin, how matter moves between stars, and how prepared we can be when we decide to meet the universe halfway. If this journey resonated, stay with us. Subscribe if you haven't, ring the bell so you don't miss the next deep dive, and tell me in the comments what you want to chase next. A rapid intercept mission playbook, a simple guide to reading comet spectra, how to photograph a faint visitor from a city balcony. I read what you write, and a lot of our best episodes start with your questions. Share this with someone who needs a different kind of space story, one that trades doom for discipline and hype for honest wonder. And if you are part of the observing effort, professional or amateur, drop your experience below. What did you see? What surprised you? What do you wish we had ready for the next time? To the mission teams who turned, pointed, scheduled and squeezed signal from noise, thank you. To the night shift observers and the folks who wrote the software that finds fast, strange movers, thank you. To everyone who paused long enough to look up and think about a traveller from a different sun, thank you. This channel exists because curiosity is still stronger than distraction. 3i Atlas leaves us with a simple line that I can't stop hearing. We're in this together, across time and stars. The universe keeps sending messengers, We keep getting better at reading them. That's the story we're telling here, one visitor at a time. Until the next stranger arrives, keep your instruments warm, your mind open, and your nights a little quieter than your days. I'll see you in the next one.